In this video, we're going to get a brief introduction to alcohols and alkyl halides. So this is our first real dive into functional groups, so functionalized alkanes, and we'll continue to see more of this throughout the course. But the first ones we're going to be talking about are alcohols and alkyl halides. Remember, an alcohol functional group, we have an R group attached to an OH. We call this the alcohol. And an alkyl halide would be RX, where X can be something like Cl, Br, F, or I. So these would be our alcohols and alkyl halides. We've already briefly discussed the nomenclature of alkyl halides. These are named as their substituents, so we would say a chloro with the numbered position, a bromo, a fluoro, an iodo with the numbered position as we would number normal alkyl substituents on a parent chain. The naming system for alcohols is a little different. So we're going to let's look at an example alcohol, for instance. So let's look at this one right here. So first, we're going to name the parent chain that the alcohol is attached to. So in this case, our parent chain would be ethane. Eth meaning two, it's a two-carbon chain. And then we would indicate the position that the alcohol falls on, giving the alcohol always the highest priority. So in this case, we wouldn't number 1, 2. We wouldn't do that. We would instead number 1, 2 with the alcohol taking priority. And we'll see that when we have more than one substituent to choose from on a particular parent chain, we will always place the alcohol numbering such that the alcohol has the lowest position possible. We would then indicate the number, so this would be 1 ethane, and we would change the ending to indicate that it's an alcohol. We change it to ethanol. So we'd have 1 ethanol. Usually when we have it on the 1 position, we can leave it off and we would just say ethanol. Sometimes when we're numbering alcohols, we put the 1 in the middle, so we could say ethan 1 all. But again, this would be redundant for something like ethanol because we have really only 1 substituent. So let's look at something that has more than 1 substituent. So we have, let's see, 1, 2, 3, 4, 5, 6, 7, and I'll put a methyl chain here, and I'll put an alcohol here. All right. So we would have to choose, our first task would be to number the parent chain. And again, this is a position where we would number either left to right or right to left. And as I was saying before, we would want to number such that the alcohol falls at the lowest possible substitution position. So we would number, in this case, we would number from right to left. So we have 1, 2, 3, 4, 5, 6, 7. So we would see our alcohol falls at the 3 position and our methyl group falls at the 6 position. Now, when we're naming substituents, we always name the alkyl or the halide substituents as normal. Those would be before the parent chain prefix. The alcohol always falls as a suffix at the end of the parent chain. So in this case, we would have our 6-methyl. So we have 6-methyl. And then we would number the alcohol position. We put it at 3. We then name the parent chain. In this case, I'll put it in black. So it's a 7-carbon chain. So it would be hept. And then we have an to indicate the ane, which means it's a alkane. And then we would have OL at the end to indicate that it's an alcohol. So we have 6-methyl-3-heptanol. And similar to this ethan 1-all naming, we could write this as 6-methyl-heptan 3-all. This is an older naming system, and typically now we see it as 6-methyl-3-heptanol rather than the 3 stuck in the middle, right next to the suffix. We can, just to hammer this home, we'll do 2 more examples. We can do this with cyclic naming as well. So I'll draw our cyclopentane rather, and we'll have a methyl, and then we'll have an OH. Again, we want to number such that the alcohol has the lowest priority, so this would be our 1 or lowest substitution. And then we're going to go counterclockwise around this cycle, so we have 2 as our methyl position and not 5. So it's 1, 2, 3, 4, 5. Now we've already seen that we could indicate stereochemistry at these 2 positions. Since we have 2 stereochemical assignments, we could indicate these as R or S. Or we could indicate these as cis or trans because there's only two of them. So in this case, one is pointing up, one is pointing down. So we could indicate these as trans. So we would start out our naming with trans. And again, we could indicate this. This is where we would put, one RRS, two RRS. In this case, it would be a 1S, two R. So we could say 1S, 2R as well. I believe that's correct. Or we could say trans because there's two of them. So we have trans, and we're going to say 2-methyl. And then we're going to name the parent chain. In this case, it's cyclopentane. So we have cyclopentane. And then we're going to name the alcohol. Oh, I forgot the number. We would put the 1 here. 1 cyclopentanol. And again, we could stick that in the middle. We could have cyclopentan 1 all. Again, since it's the 1 position, sometimes this 1 is left off. So we could say trans 2-methyl cyclopentanol. But to be formal about it, we would indicate that it is at the 1 position, and we would indicate that as 1 cyclopentanol or cyclopentan 1-all. Just to do one last example with a halide substituent. We have this fluoroalkane here. We would number it such that the alcohol has the lowest substitution. So we put the 1 here, 2, 3. We have a 3-fluoro and a 1 alcohol. So we'd start with 3-fluoro. And then we'd indicate the position of the alcohol. We have 1, and again, this would be optional. 1 propan, and then we indicate the alcohol, propanol. So we'd have 3-fluoro, 1 propanol, or 3-fluoropropanol, depending on how formal you're being about the naming system. Now, there are different classifications of alcohols and alkyl halides that we see, and it's often based on their substitution patterns. So if we have, for instance, H3COH, this would be methanol. If we have a methyl group attached to an alcohol, we call this a methyl alcohol, methanol methyl alcohol. If we start introducing an alkyl substituent, so say we have ethanol, so this would be ethanol, where we have it attached to an R group, we would call this a primary alcohol. Primary meaning that the carbon that is attached to one other carbon. So this would be we would call this a primary alcohol. If we introduce more branching, so this would be isopropanol or 2-propanol, we would call this a secondary alcohol, meaning that this carbon center that's attached to the alcohol is attached to 2 other carbons. So we would call this a secondary alcohol. Following this trend, if we attach it to one more carbon, this would be T-butanol. We look and we see that this carbon that is attached to the alcohol is attached to 3 other carbons, so we would call this a tertiary center. And this can apply to both alcohols and alkyl halides. We have methyl, primary, secondary, and tertiary. And we're going to be examining the effects of moving from methyl to primary to secondary to tertiary, as well as other effects that alcohols and alkyl halides can have in the rest of this video. Now you can imagine that going one more step from this, we could have a quaternary center. So if this carbon in the middle is attached to 4 other carbons, we would call this a quaternary center. This can happen for carbon and nitrogen-based centers, but it cannot happen to alcohols because alcohol is going to be, that O is going to be one of the derivatives of the central carbon. Now, if we examine the bonds in alkyl halides and alcohols, so drawing a methyl alcohol and a methyl halide, so we have a methyl alcohol and we have a methyl, we'll call it a methyl chloride. If we examine the methyl alcohol, methanol, and this would be methyl chloride, or chloromethane rather, we see that the dipole moment points towards the OH or the Cl or the whatever halide is substituted here. So because we have this molecular dipole, this dipole means that we have strong intermolecular forces. And that's going to be that's going to affect the physical properties of alcohols and alkyl halides quite a bit. And we'll see that the more substituents, the more alcohol or halide substituents we have on the carbon center, the stronger the effects of these IMFs are going to be. So as you can imagine, the more substituents we have um, on a particular center, the higher the melting point and the boiling point. And in fact, moving from an alkane to an alkyl halide to an alcohol will also increase the melting point and the boiling point. So, for instance, if we look at, we can look at propane, and then we have fluoropropane, and then we have, fluoroethane, and then we have ethanol. If we examine the boiling points of each of these, the boiling point of propane is negative 42 degrees Celsius. The boiling point of fluoroethane is negative 32 degrees Celsius. And the boiling point of ethanol is 78 degrees Celsius. And the reason for this is because we're increasing the number of increasing the strength of the intermolecular forces, moving from an alkane to a fluoroalkane to an alcohol. So if we examine the alkane, we're relying solely on London dispersion forces to hold these molecules together. Very weak induced dipole forces, which is why that this is such a low boiling point. As we move to a fluoroalkane, we have both London dispersion forces and we have a dipole. Now we have a permanent dipole right here. So this dipole force is going to increase the boiling point quite a bit and increase the intermolecular forces that we have within a sample of this molecule. Moving to ethanol, we have both London dispersion forces and dipole forces. And because we have this OH group, we also introduce hydrogen bonding. So hydrogen bonding is quite strong, and we see that it increases the boiling point from negative 32 to 78 degrees. Again, here's that dipole. And then we do have that hydrogen bonding network that can form. If I draw another molecule, we can have a hydrogen bonding network that can form between adjacent samples of ethanol or adjacent molecules of ethanol that hold these molecules together quite a bit more strongly. Another trend we see is if we if we increase substitution on a molecule, so say we go from CH3Cl to CH2Cl2 to CHCl3 to CCl4, we're going to see the boiling point increase as well. Again, we're increasing the strength of the dipole on the molecule, and in turn, we're going to increase the intermolecular forces holding those molecules together, and as a result, we increase the boiling point. So we just see, to give numbers to this, chloromethane is negative 24 degrees Celsius. Dichloromethane or methylene chloride is 40 degrees Celsius. CHCl3, this is chloroform, this is 61 degrees Celsius, and carbon tetrachloride is 77 degrees Celsius. So we see as we go from 1 chlorine to 2 chlorines to 3 chlorines to 4 chlorines, we are increasing the boiling point at each stage in order to increase the dipole forces and increase the boiling point. Just a few more facts about alkyl halides and alcohols. Alkyl halides are often insoluble in water, and that's just because the dipole is not strong enough to be soluble with the strong dipole in water. For alcohols, C1 to C3, meaning methyl to propyl alcohols, are generally soluble in water, and then greater than C3, so butyl alcohols and above, are generally insoluble, and that's just because as we extend this chain longer and longer, we are increasing the length of the what we call the greasy portion of the molecule, the nonpolar portion of the molecule, which is insoluble in water. In terms of density, we have alcohols, alkyl fluorides, and alkyl chlorides that are less dense than water. So if we're drawing a density diagram, we have alcohols, alkyl fluorides, and alkyl chlorides that are less dense than water. Then we have water. And then more dense than water, we would have alkyl bromides and alkyl iodides. This is general. We do see that with more substitution on alkyl chlorides, they can move down to be more dense than water. But in general, the alkyl bromides and the alkyl iodides are across the board more dense than water.